Let's continue our study of Chapter 11, talking about planar graphs. If you'll recall from lesson 11.1, we did talk a little bit about planar graphs, and we said a graph is planar if it can be drawn without any crossing edges. So when we did this, we looked at a complete graph of K1, and obviously that's planar. And then K2, we said, well, that can be planar. And then we said, well, K3 is planar. And then for K4, I gave you these two representations. And so K4, while it is not planar here, it is a complete graph, not planar because we have overlapping lines. I can draw K4 in a planar fashion, as I've shown you here, or in another way. This is also K4 in a planar fashion. Now again, it's legal because this is a vertex, whereas this guy did not have a vertex, and therefore that is why it was not planar. So we know through K4, yes, we can draw a planar graph. The question then becomes, what about K5? And so again, you can do some guess and check here. And I can say, well, this one is fairly easy to connect to everything. To connect the next vertex to everything, I can go this way to get to the first vertex. This one's very easy. This one I just have to loop around a little bit. To get this guy connected, I can go straight across here, but now I'm stuck because I'd have to hop over this guy to get over here. And then again, this guy works, but to get back to the other guy, I'd have to hop and come over here. So the question then becomes, does that tell me definitively that yes, it's not planar? No, that just means maybe I just suck at drawing, which of course I do. But this one, in fact, K5 and on are not planar, but we're going to talk about how to determine that more than just guessing and saying, well, I couldn't come up with one. Let's look at another kind of graph. This one's called a bipartite graph. And essentially in a bipartite graph, we have two groups, and everything in one group connects to everything in the other group. But if two graphs are two vertices are in the same group, they don't connect to one another. So most often in a bipartite graph, we'll just show one up here before we look at the examples I have drawn out already. Let's just look at K2, 2. So the way that we draw this is we say how many are in the first group, how many are in the second group. So obviously this guy can connect to both, and this guy can connect to both. So that's one way to draw K2, 2. What we also find, this is here K2, 3. As you can see, I've drawn it one way, but then I've drawn it a little easier way by saying, let's take this guy and just pop it over to the other side, and then we can see both of these are representations of K2, 3 that are planar. My question then is, what bipartite graphs can be written planar and which ones cannot? So I've already shown K2, 3, I've shown K2, 2, and really K2 anything I want would work because I could just draw it like this. So if I had, you know, many more dots in here, it wouldn't change anything because I can still draw it in this fashion. And if you'll notice, I'm still not crossing any lines. So we know K2 anything works. Obviously K1 anything works because it would just be a graph that looked like this with however many vertices over here. So then the question is, what about K3, 1? Well, K3, 1 is like K1, 3, and we know that's possible. What about K3, 2? Well, K3, 2 could look exactly like K2, 3, and we've already shown that K2 anything is possible. So what about K3, 3? Let's see. running out of room on my tiny little slide. 1, 2, 3, 1, 2, 3. So can I connect my first vertex to everything? Yes. Can I connect my second? Well, I can. Again, I'm not connecting straight up because those two are in the same group. Whoops, got a little erase happy. This guy can connect over here, and this guy can connect here. And to get to that last guy, I'd have to sort of loop around. And then for my last one, I probably should have switched colors. For my last one, I can get to this one quite easily. And I can even get to this guy, but I'd have to hop over this one to get to that last one. So K33, I haven't been able to come up with one. What we find is, in addition to K5 and on being nonplanar, that K33 and on are also nonplanar. And that brings us to Kuratowski's theorem. Kuratowski essentially says that a graph is nonplanar if and only if it contains a subgraph homomorphic to K5 or to K33. So we've talked about isomorphic. It has the same number of edges, same number of vertices, it has the same cycle structure, all of those things. So it's isomorphic, and homomorphic says essentially I can do a little subdivision and come up with the K5 graph or the K33 graph by adding vertices to get our graph in question. So subdivision is a very easy example. Here's my edge AB. All I did was add this guy. So now I have an edge AC and I have an edge CB. And so essentially what we're saying is we could redraw a graph and come up with something that is homomorphic to either K5 or K33. This is one example that I have stolen from your textbook. And so the original graph is something called a Peterson graph. And the question is, can I redraw this in a planar fashion? Well, by going through a very long and detailed process that I'm not going to go through with you because I just don't feel it's worthwhile for us to do that. If you are very interested, I have included a Trev Tutor video in your class notebook that takes you through how to redraw a graph into a subdivided graph and the process that it requires. But essentially, I can see that this graph can be redrawn into what is a K33 graph. And a K33, as we know, is nonplanar. So this is isomorphic to K33. And therefore, and we can see we did some subdivisions here. So I've got some of these segments that are in my original K33 that just happen to have some extra vertices on them. That is the process of subdivision. So again, don't think that I would very quickly be able to get from here to here. It would take a lot of drawing and redrawing and erasing and redrawing, etc. to come up with it. But essentially, that is the process that would be involved in making those graphs homomorphic to K5 or K33. Again, that process is long, it's confusing, it would be very time-consuming, and so we're going to talk about Euler's theorem because Euler discovered a way to determine if a graph can be drawn as planar using the sum of regions created by a planar embedding. It won't tell us what the graph looks like, but it can tell us whether or not it's planar. So Euler's theorem essentially says that if I have V representing the number of vertices, and E representing the number of edges, and R representing the number of regions, and we're going to do an example and I'll show you what I mean by regions, then we can conclude that V minus E plus R is equal to 2. So the number of vertices minus the number of edges, add the number of regions, it should equal 2. If it doesn't, not planar. If it does, it's planar. So let's look at K4. And again, we've drawn K4 a couple of different ways, and I've shown you both ways here. Looking at my planar version, this is my K4 planar, obviously. We've looked at this several times. We can see that there is 1, 2, 3, 4 vertices. There are 1, 2, 3, 4, 5, 6 edges, and regions are found essentially by saying here is a space that is confined, here is another space, here is another space, and then here's the infinite space that is everything else. So there are 4 regions, and so I'm adding 4, and as you can see, 4 minus 6 plus 4 does give me 2, and that is what I wanted based on Euler's theorem. If I look at the K4 version that was non-planar, we can see that, again, I'm still going to have the 4 and the 6 because that's what I'll need for a K4 graph. But the number of regions is 1, 2, 3, 4, 5. And that math doesn't hold. And so that is not a planar graph. So you might be thinking, as I have, that, wow, that's not helpful at all because I have to actually be able to draw it planar in order to show that it is planar. Because obviously K4 can be written as planar, but if I drew it wrong, I had the wrong number of regions and the math didn't work. However, there are some corollaries that come from Euler's theorem that can help us. So if we're looking at a planar graph, again, V is the number of vertices, E is the number of edges, and we have at least 2 edges, and we have R regions. We can also say that these 2 inequalities are true. That 3 times the number of regions is less than or equal to 2 times the number of edges, and again, one that doesn't use regions and just uses the edges and the vertices says that the number of edges has to be less than or equal to 3 times the number of vertices minus 6. So let's look at K5. Now we already talked about the fact that K5 isn't planar. We had a very silly attempt at trying to make it planar and that didn't work out. But let's look at the math behind that. Here I have the number of edges is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, nope, just 10. Sorry, I think I counted one twice. Oh, there we go. I counted that one twice. So there's 10. So number of edges is 10. What are the number of vertices? Well, it's a K5, so I don't have to do any silly counting. There's 5 of them. 3 times 5 is 15. 15 minus 6 is 9. That does not hold true, therefore K5 is non-planar. Now the good news there is I didn't have to count regions. Obviously I'm a horrible counter because I just counted the number of edges wrong. But I didn't have to count any regions, so it doesn't matter how I draw it. I can use this to determine whether or not it's planar. Hopefully you are asking yourself, well, that's all well and good, but where did that come from? Don't just take my word for it, because I gave you these and I didn't say where they came from. So let's talk about where they came from. We know some things about graphs. This is the first one. We've talked about this for a while. The sum of the degrees is equal to 2 times the number of edges, because every time we add an edge, it adds 2 degrees, essentially. One on the in, one on the out. So whether it's directed or not directed, it really doesn't matter. We know that it's going to be even. And we might have seen this as 2e instead, which is the same thing because we're using lowercase e to represent the number of edges. Then we talked about regions, and we said each region, and again, region came from some enclosed space or the exterior of our figure. We know that each region must have at least 3 edges. So here's an example of a region with 3 edges. Obviously I could have more than that. This would be a region that has 4 edges, but it's at least 3. So we know that each region must have a degree of greater than or equal to 3. Hopefully you're with me so far. Therefore, I can say that 3r, 3 times the number of regions, has to be less than or equal to 2e. And that's really just by substituting 2e down here. So 3 times the number of regions is less than or equal to 2e. So that's where this guy came from. But that one wasn't super helpful because, again, I'd have to know regions, and in order to know regions, I'd have to have a figure. So let's make it more helpful. Let's find where this came from, which doesn't require me to know regions. So by Euler's theorem, and again, I didn't go through the proof on Euler's theorem, but you're welcome to look that up. We know that this is in fact true. I can take everything times 3 because that's just simple algebra. And by substituting, I can say, instead of using this equal sign, let's replace 3r with 2e. And now, instead of an equal, I have an inequality. And from here, I'm saying, well, hey, minus 3e and plus 2e actually combines to minus e. And then, let's get e by itself, and that turns into e is less than or equal to 3v minus 6. And that is the most helpful corollary from Euler's theorem. So Euler's theorem, obviously great for regular graphs. We haven't talked about now how this is going to work for bipartite graphs. Bipartite, remember, that means we have 2 sets of vertices. So if G is planar and bipartite, then we have 2 very similar corollaries. And again, we can use those to show that K33 and on up, essentially, is non-planar. So again, using e is less than or equal to 2v minus 4. The number of edges would be 9. 3 times 3, which is 9. And the number of vertices would be 6, because 3 plus 3 is 6. And 2 times 6 is 12, minus 4 is 8. 8 is not greater than or equal to 9, therefore K33 is not planar. Again, don't take my word for it. Let's look at the proof. The proof says, since G is bipartite, we know each region must be surrounded by at least 4 edges, and so therefore now we have 4r is less than or equal to 2e. And then from there, the proof is really just follows exactly what we did for our other proof. By substitution, multiplication, and simplification, we come down to where e is less than or equal to 2v minus 4.